Welcome everyone. My name is Jacek Komorowski. I'm working on Warsaw University of Technology in the Faculty of Electronics and Information Technology. And today I will talk about similarity learning using deep neural networks. So first, I will do a kind of an introduction why we even need the similarity learning and what can we use it for, what kind of problems we can solve using this similarity learning approach. Well, to start with, let's do a quick introduction. So basically, currently, in the recent years, the neural networks made a big progress in terms of the various classification approaches. Like if you classify images or audio data, there was a huge progress during the last 10 years. Can be visualized by results of the large-scale visual challenge when there is a challenge run every year when the task is to classify images, whether they contain a zebra, a cat, car, or a table. And we've got, in this challenge, we've got like 1,000 categories of objects, and the task is to classify these images assigned to a correct category. Top 5 error rate, that's basically the solutions provided to the challenge, return probability of the, let's say, 5 most probable classes, and if the true class of the object is within this top 5 most probable classes, we've got a success. So we can see that from the 2010, the error rate decreased by like 10 times. From 28%, recent submission last year was like 2.3%. In classifying this huge data set of images with thousands of categories. And we can see, like on this example, that the results of the best solutions that are based on convolutional neural networks are pretty good. We've got this kind of a container ship. The network thinks, okay, it's container ship with high probability. It also thinks maybe it's, lifeboat, possible, or drilling platform with very small probability, but it also looks kind of a drilling platform. So all of these predictions of the neural net are quite reasonable. And basically, this huge progress was possible mainly by 2 reasons. First was that we've got now efficient neural network architectures. For visual information, for images, we've got these convolutional neural networks, and there was a number of architectures presented recently, like quite simple VGG convolutional neural network set of architectures, more complex architectures like Google Net, also called Inception, or ResNet, which is quite deep network with hundreds of layers and residual connections. And they each, provided better and better results and allow to classify images with really, really high accuracy. You can use, these architectures in your own projects. You can use, train them from scratch, or you can use the pre-trained architectures. And, in modern deep learning libraries like Keras, it can be done, in 20 lines of code, if you've got the data, of course. And the second contributing factor to this great success was large data sets of labeled data. So there are large data sets, publicly available, containing millions of images, labeled images, like ImageNet, which contains 40 million of labeled images from 20,000 categories. So we've got images of zebra, cats, tables, dogs, and we've got hundreds of these images. Or Open Image Dataset, 30 million of images, 20,000 categories. So for average category, we've got like few hundred images, labeled images, few hundred images of a car from different point of views. But this approach that we take, a huge data set with different classes of objects and few hundred or few thousand elements from each class is not always feasible. There are many scenarios when it does not apply. For example, we've got like pedestrian identification problem when we want to match image of a person captured by one CCTV camera and find, for matching images from other CCTV cameras, from other security cameras. We don't have hundreds of thousands of images of a single person. We've got only one, two, maybe a few. So we cannot train a classifier, providing them, I don't know, images of 10,000 persons with only 2 images per person and ask them to classify these persons. Results would be terrible. And even if we do that, then in practice, if we train such classifier, then next day we capture images of next 10,000 or next 1,000 persons. And what we shall do? Shall we retrain the classifier from the scratch to classify the new persons and, wait, I don't know, 1 or 2 days for the training to finish? It's not feasible. The same is the face recognition. We usually don't have hundreds of thousands images of the face of a single person. We've got only 1 or 2. If we've got our, face recognition system built into our mobile phone, we don't want to take 100 images of us, to be able, so the phone can recognize us. So this scenario, when we've got very large number of classes, or even unlimited number of classes, because of face recognition, well, we have, number of people, it's huge. We cannot use simple classification approach. The other scenario, when the simple classification approach is not working, is this, well, when we search for similar things, like we search for similar images. We provide an image and want to find similar images. Here we don't have a category of classes of categories assigned to the object. We just provide an image of an object and can be, unlimited variety of objects, and we'd like to find something similar. A popular application is, for example, searching for similar fashion items. We've found something that we like, made a picture of some, T-shirt, want to provide it to the system, and want the system to find, similar offers in web shops. Or there can be some applications from other domains, not visual domain, like we want to match resumes to job descriptions, for example. Also, we don't have classes, categories. We've got, the resume, the CV, and we want to find matching job offers. So how to solve these problems? Well, and here comes the concept of similarity learning. Basically, instead of learning how to classify the input, it can be image, input image on a sentence, we want to learn how to inputs are similar. We want to learn the similarity between 2 inputs. And this concept of similarity learning is closely related with distance metric learning, that basically is, the old task that we want to learn a metric, some kind of metric measure of distance that assigns small distances to similar objects, like to images of face of the same person, and large distances to different objects, like images of face of different persons. There are a number, this is the old problem, and there are a number of traditional approaches, like principal component analysis, like linear discriminant analysis, neighborhood component analysis. But we can also use, especially for visual data, for audio data, for natural language sentences, we can use deep neural networks for this, to solve this problem. And basically, the idea is to use the neural network to transform the input data, it can be an image, to some low-dimensional representation, often called an embedding, which is actually a vector, in real-valued vector of some fixed length, usually much shorter than the length of the original image. And then distances in this embedding space actually represent similarity of the objects. Just to visualize how it looks like, so basically we've got our input space. It can be images, it can be some encoding of natural language sentences, and we use neural network to basically transform this image, and this input space has quite huge dimensionality. So if we've got like this input image 300 by 300 by 3, it's 270,000 dimensions, vector quite huge. And we use neural network basically to encode this input element into some lower dimensional vector in this embedding space representation space. But of course, we want to encode it, so that this encoding is reasonable. It has the properties that interest us. So basically, we want this encoding. So the encodings of similar objects, like, these cars, they are close in the representation space. Encoding of different objects, like car and ship, they are quite apart in the representation space. To produce some encoding, we can actually use, a neural network of our choice, basically. So if this is a visual information, we'll likely use convolutional neural networks. If this is natural language sentence, we'll use probably some kind of a recurrent neural net. It's problem dependent. But as the result, we've got this embedding, low-dimensional embedding, which we can efficiently compare with embeddings of other elements. And if we have such representation, how can we use it then to solve our problem? Well, let's talk about on the example with this face recognition. So we've got, images of the persons in our data set, and we've got a query image for which we would like to find the identity. So what we do is that we use this convolutional neural network encoder to compute the low-dimensional representations of the images in the data set. So for each image in the data set, we process once through the network, and we compute their embeddings, called f(x1), f(x2). And then we've got a query image. We would like to find identity of this person. We also fed it through the network, computed embedding, fq, and then search for the closest embedding in the embedding space. So we've got this embedding of the query image and search for the closest embedding in this embedding space. And basically, these are relatively low-dimensional vectors, and searching for closest vectors in the Euclidean space, it's not hard. Well, depends on the dimensionality of this database. If it's not huge, if there are only hundreds or thousands of elements, we can just compare this element with each of them and find the closest one. Using some Euclidean distance or cosine distance, depending on our problem. If there are a lot of these elements, like millions, and we are searching for similar images, and we are going to run, hundreds of searches per minute, we need something more efficient. So there are efficient libraries for approximate nearest neighbor search, like Flan. So we don't have the nearest neighbor, but sometimes we can have the nearest neighbor. Sometimes we can have the second nearest element. But it's quite fast. So this works good, but the key question is, okay, but how do we train the network, this component, so it produces the embeddings that got the desired properties, So the similar objects land in the, we've got similar representations. And these similar objects have these similar representations that are far apart. And there are a few ways to do it. One of the most popular is, just to reiterate, this is the required property, that embeddings of semantically similar elements, like similar faces, needs to be close in the representation space. Embeddings of distant elements needs to be far away in the representation space. One of the most popular approaches, how to do it, is to use Siamese networks. The name comes from the, Siamese twins, which are twins that are connected together. So here we've got Siamese networks. When we've got two identical neural nets, in our example, it's convolutional neural net because we are processing graphical information, visual information. But if you are processing like natural language, you will likely use recurrent neural net. So these are two identical modules with shared weights, which process pair of examples. And we would like to train this network so when it has, when the input is pair of similar things, like images of the same person, it computes these embeddings and computes the distance between. So this part computes the embeddings of the input elements, and this is basically Euclidean distance between these embeddings. This is the second norm of the difference between these two vectors. So Euclidean distance. So if we fit similar elements, images of the same person, we would like this distance to be low. If we fit dissimilar elements, like images of different person, we would like this distance to be high. Well, how to train the network to behave like that? Basically, construct the proper loss function, yeah, that will, during the learning, will optimize the weights of the network that it provides as we want. And the most popular loss for training Siamese networks is this contrastive loss, which consists basically of two terms. So one is the term for positive example. So for positive pair, when we fed similar images, the images of the same person, we would like these embeddings to be close. So we construct that the loss is basically the squared distance between the embeddings. Yeah, so the higher the distance between these embeddings, the higher the loss, and it goes up quadratically. So when you train a network with this loss, it basically wants to make embeddings of the same elements as close as possible. Of course, this is not enough, because if we only use this term, then, the network will learn to produce embeddings that are all the same, actually, of each input element. Yeah, if, for example, every element is mapped to 0, well, perfect. Yeah, this part of loss is 0 because, everything is similar to everything. So it's not good. So we also need a second term with the loss function, which is loss for the negative pair. And this loss actually pushes the embeddings of the dissimilar elements apart. In practice, we don't want them to be, infinitely apart. It's sufficient that they are at least some fixed margin m apart. So basically what this says is that, okay, this is the distance between the embeddings, and if this embedding is actually higher than m squared, then, if it's more far away, doesn't matter, yeah? If it's at least as far as m, loss goes to 0, and we are happy with it. So how we will proceed? Basically, we train the network, we provide them alternatively pairs of similar and dissimilar elements. So we sample a pair of similar elements from our training data set and compute this positive loss on this pair. Then we sample a pair of dissimilar elements from our training set, compute this loss, and then, proceed a standard neural network training procedure using gradient descent. So we actually fed this similar and dissimilar element in batches. Usually we do a mixture like 50% of similar pairs, 50% of dissimilar pairs. Each batch element is a pair of images. We provide these batches to fed the batches through our Siamese net, compute the gradient, use backpropagation then to update the gradient. And using the modern neural network, deep neural network frameworks like Keras or PyTorch, we can do it with, like 20, 30 lines of code. So it's pretty easy. But this approach, Siamese networks are popular, but they've got one, I would say, drawback, which is that here we need to specify which elements are similar, which are dissimilar. This may be fine for face verification because, well, either there are two images either of the same person or a different person. But if you would like our network, for example, to train it to search for similar fashion items, we've got these degrees of similarity. We can tell that, okay, one item is more similar to the other than the third one, but we cannot tell, hardly that, okay, this is similar, this is not similar. There are these degrees of similarity, and we cannot encode this using Siamese nets. So another popular architecture for similarity learning, or learning these embeddings that got desired properties, they are triplet networks. And these are also very popular in practice. Actually, they are used in many scenarios, even for the face verification or face recognition. When we've got this hard measure of similarity, we also sometimes use triplet networks, and in some papers, authors claim that they perform better than Siamese networks. So it's also worth to try this one. It's also quite easy and comparable to Siamese network. The only difference is that we've got here 3 kids on the block. So we provide triplets of elements to the network. We provide kind of a baseline element. This is called anchor. In TripletNet papers, this is called anchor element. We provide one positive example, that is an element that is kind of a similar to the, or more similar to the anchor, and negative example element that is less similar or dissimilar. If we are, if we are looking to search for similar fashion items, clothing articles, we would provide one item here. Here, we, as a positive example, we put something that is more similar. Here, we put something that is less similar. Yet again, we've got here 3 modules, but these are identical also networks with the shared weights. Architecture is domain-dependent. For images, we'll have convolutional neural networks. We compute the embeddings of each input element, and then we compute the Euclidean distance between these embeddings. Actually, here it's squared Euclidean distance on this plot. And we want to train the network in that way that the distance between this positive example and anchor is low or lower, and distance between anchor and negative example is higher, higher by some margin. How to achieve it? Of course, by designing the proper loss function, and the very popular loss function is the triplet loss. His reference to the paper that introduced this loss. It was used in the context of face recognition and clustering. And the triplet loss actually, so here we've got only one loss term because we don't have pairs of negative, positive examples. We've got a triplet that contains both negative and positive example. And it consists of 2 terms. This term depends on that anchor and positive example. And basically, the higher it is, the higher is the distance between anchor and embedding of positive example, the bigger is the loss. So the loss is driving these 2 embeddings together. And this part depends on the distance between the anchor and negative example. So it's driving this embedding of negative example far away. And also we want this difference, we are happy if this difference is larger than m. So hence the margin. So if the distance between anchor and negative example is larger, or squared distance, is larger than squared distance between anchor and positive example, larger by this margin m, the loss goes to 0 and we are happy. Negative example, embedding of negative example is far away than embedding of positive example from the anchor. And then we can use our favorite deep learning platform like Keras, PyTorch, to run optimization in this fashion. And then when we train the network, we just do a little bit of surgery, just take this one module out of the trained network and use it to compute embeddings of our input data. And then, as shown on the previous slide, we can use these embeddings to search for similar items or to compare, to find similarity of elements. This looks quite easy, but there's one, I would say, very important thing that if you implement this in practice, you need to remember. As always, that some theory can be nice and easy, but then in practice there are a lot of issues that you need to consider, and it's not always working, as good as you want. And this is called hard negative mining. If you look for papers regarding triplet network or samiznet, you will often find it. And also in practice, if you will implement your solution, you will need to take care of this. And what's the problem here? Basically, here's the triplet loss, just written again. So basically, if we've got our data set, say, of n people, and we've got 2 images of each person in the database. So the number of positive examples is, linear with the size of grows linearly with the size of data set. If we've got, n pairs of images of each person, so we've got n positive examples. Number of negative examples goes quadratically, actually, with the size of data set. So because we've got, for each person, we can take n-1 negative examples times 2, because the n-1 other persons. And then all possible pairs is n, it's proportional to n squared. So we've got a huge imbalance, actually. We've got quite a little number of positive examples and huge number of negative examples. And if we take a naive approach where we, take a positive example, feed it to the network for training, then randomly choose a negative example, then often these negative examples will be quite easy for the network because, we take two images of the random person. They look quite different. They've got, different hairstyle, completely different face shape. So it's easy to network to differentiate them. And the network is not learning. Whereas we are looking, we want the network to learn these subtle differences that differentiate people, subtle changes maybe in the nose shape, lips, eyes. So we need to somehow to guide the network and profit to the network, these hard examples. So the network can learn on them. And there are different strategies to do it. Basically, one of the popular is that we do it in this so-called online batch online hard examples mining, where we fed a batch of data from our embedding network, we compute the embeddings, and then having these embeddings, we look for the hard examples. We look for the embeddings of images of face of different persons, but that they're close. And these are hard for the network because network at the current stage thinks, that they are maybe similar, but they are not. We know that from the ground truth. So we take these hard examples and, use these hard examples to construct training examples for the network. And then we fed these hard examples, hard negative for the network, so it learns to find these subtle differences. Some care is needed with this, mainly because, if we provide to the network very hard examples, sometimes there are outliers in the data set. So we choose the hardest example as can be in the data set. The network will be often confused and will learn nothing. Because there will be outliers, it will not be able to start learning. So it requires some care and attention, but it's good to refer to the papers, how the author suggests to deal with it. But definitely, if you implement this in practice, you will need hard negative mining. That's for sure. I don't have much time, but just quick example to see how easy it's implementing Keras, and later there are links to the working examples you can run on your own. Euclidean distance. So Keras is, if you don't know, deep learning platform. I would say good for beginners because it's quite easy and you can implement and run your model in few lines of code, although it's not as flexible as PyTorch, but good for starting. Euclidean distance, so it's defined as the operation of so-called tensors. This tensor describes the data that goes through the neural network. It's one line of code, actually. And what it computes is difference of two vectors. We take a square, sum it along the dimensions of the vector, and take a square root. Classical Euclidean distance, nothing simple. And this is contrastive loss for the Siamese network. On the example I've shown you, contrastive loss consists of two terms, positive and negative. Here they are just glued together. This y is parameter that says if it's positive example, y is equal to 1. So this part for positive example becomes 0. So here we've got this part, and this is the positive loss. It's mean of the basically square distance between elements. For negative, if we've got a negative example, y becomes 1. So becomes 0. So this is 0 because y here. This is 1, and we take just this margin minus the distance squared. So exactly as as was shown on the formula previously. We define the network. This is a very simple, fully connected network. Of course, for real-life usage, you will define here some convolutional neural network, or use the network which is predefined in the library. So easily in Keras, you can import, train AlexNet, for example, or GoogleNet. We define the network, and then, in these comments, basically, we create the Siamese network. So we define the network that it's got two inputs, pass each input through the same network. Then there's a lambda layer that computes the Euclidean distance between the output of these two layers. So it corresponds to the picture I've shown earlier. And then for the training, there is the part that is with 3 dots. It's creating of a training data, which is, you need to implement it by yourself, depending on type of the data you've got, basically to generate the pairs of data. And then when you've got training pairs defined, you compile your model, using this contrastive loss, Siamese loss, and you run the model fitting, actually, training your model, which you do it with one line of code. And here at the end are just, a few URLs for web pages where we've got a simple kind of introductory Siamese neural network models with the code. First three are in Keras, the last one is in PyTorch, I think. So you can experiment for yourself. So thank you for your attention.
Any questions?
Thank you for the presentation. One question: when you're defining the data set, the training set, do you pre-compute all the pairs immediately, or do you per epoch change the pairs of similar and non-similar?
No. Usually it's not pairs are not defined earlier, but online during the training, because you want to mix them. Usually you don't want to pull the same pairs in batches. So especially for negative pairs, you want kind of to sample them. Of course, having in mind this hard negative mining necessary.
One more question, if possible. And so for this hard negative training, so just to make sure I understood, you compute all the embeddings, and then you cluster them, and then from those you generate the...
Yeah, maybe not all, because you may have a huge data set. So what is usually done, you do you take a batch of data from your training data set. Maybe it can be random, or it can be, you can take batches sequential. You compute embeddings for all elements of the batch, and then having these embeddings computed, you look for the hard negatives, so the elements that that is similar or from different class, but got close embeddings. And this is, where your network makes mistake. And you take them either to construct, to put them in the triplet loss or in this negative Siamese loss. So not all data set, but take a batch, compute embeddings, so run it through the one module of the network, compute embeddings, find the hard negatives, use it to train the network. And then iteratively, loop until your network is trained.
Thanks a million for your presentation. I have a question, actually, regarding the calculating distance between the embeddings. Seems like you have to calculate many distances for each pair of embeddings. So I was wondering, how is it in terms of computational expensive cost? I'm trying to think about how we can speed up the process of calculating each distance in order to find out which one has the closest proximity.
Yeah, but you are talking not about network training, but when using the embedding to search for the closest element.
Yes.
Yeah?
Yes.
So the naive approach when you compare the embedding of your query element with each element in data set takes time. So it's fine if you've got thousands of elements, but there are libraries that these are, search for the approximate nearest neighbors libraries, and they can efficiently search for nearest neighbors in Euclidean space. And they, if you've got the data set of millions or tens of millions of elements, you can use these. One of the libraries, for example, Flan, which is quite old, and I know that there are some new ones, for example, from Facebook, which speed that up. Of course, then you don't have, 100% accuracy. Sometimes it will return element that's not the closest, but maybe the second closest or the first closest is approximate. But with high accuracy, it returns the closest element, and it's really, really fast. Yeah, prototypical networks also, because there are many extensions to this, like prototypical networks. Actually, I tried on one problem prototypical networks, but they were no better than triplet networks, which was quite a surprise for me, because these prototypical networks, actually, they optimize the loss function on the entire batch and want to actually improve results of the nearest neighbor search. Yeah, but for my problem, it was not, much beneficial. So I think it may be problem dependent. For some problems, these prototypical networks may work better. For some triplet networks, I don't think there's a, sharp answer on this. I'm not sure.
Sorry, we don't have time to more questions. Thank you.
Thank you.